Hello grade 8, welcome to lesson M1b, but before you start this lesson, you've got a warm-up. And so if you've not done the warm-up already, pause the video, pause, do the warm-up. So here are the answers for that warm-up. Solid different than gas because solids have definite shape and volume where gases do not. Magnification of these in this microscope is 400 times. The cost of running the 2-watt bulbs is 6.28 cents. Now it's 2 of these bulbs, and so that answer should actually be double. So probably 1.2 cents. And how far the cart moves, it would be 8 meters. So I'm assuming that you have watched the Eureka videos. We're now taking a look. This is, I believe, page 10 in your unit book. Work input and work output. Now, when you do work on a lever, the machine does work on a load, right? And so if we think back, we have a lever here. We've got a load. We're actually putting the effort here. Work is done here, and then work is done on the load, right? And so the work that we do, this effort, is known as the input work, where the machine does to the load. So this side here, that is known as the output work. And your lever is really just the simple machine. Now, the amount of work done here is never less than the amount of work done here. The machine can make it easier because they're going to change the amount of force that you're actually using, or changing the direction of the force. Now, there are some reasons why we may also want to wind up by using more force rather than less, but we'll get to that in a moment. The comparison of these forces produced by the machine compared to what is applied by the machine is known as the mechanical advantage, right? That mechanical advantage, and that is what mechanical advantage is. So the smaller the effort force compared to the load, the greater the mechanical advantage. So if we take a look at what is the formula for mechanical advantage, that's going to be the force on the load. This is also, again, known as the output force, divided by the force on the effort, or the input. So, if in this lever I were to apply, let's say, 2 newtons of force, and that generates 4 newtons of force this way, we get 4 over 2, that gets you a mechanical advantage of 2. Now there's no units, as this is a ratio. However, if the fulcrum is long enough, you can wind up actually moving the world according to Archimedes, because the longer this arm here, the more mechanical advantage you're going to be able to generate. So taking a look at a few quick questions, given effort force and load force, this didn't type great. The way it's written on your formula sheet is the force on the load divided by the force effort. You can actually just bring this into that kind of triangle that we've discussed, where this will be the load, this is the effort, and you're looking for one of these things to set it up. But if you've got 2 newtons of load and 10 newtons of effort, right? Mechanical advantage is going to be, therefore, 2 divided by 10. That gets you a mechanical advantage of 0.2. Oh, sorry, 0.5. to 0.5. Okay, if we had an effort of 44, load of 110, the mechanical advantage is going to be, again, load divided by the effort. 110 divided by 44. That gets you to a mechanical advantage of 2.5. Now, what if you're given mechanical advantage and the load? Well, in that case, what you're going to do is using your triangle, you're going to finding the effort means it's going to be load divided by mechanical advantage. These are the other two that are left. So with that in mind, we're going to take that effort, which is the load of 36 newtons divided by 9. That gets you an effort of 4 newtons. Similarly, if we've got that mechanical advantage, the load and the effort, but if you're looking for the load, you're going to have the mechanical advantage multiplied by the effort. So we're going to take that mechanical advantage, which in this case is simply just 1, multiplied by 13 to get the load. In this case, well, the load is also going to be 13. Now, as mentioned before, the length of the arm will give you an idea of exactly how much mechanical advantage you have. The greater the advantage, you're going to actually wind up trading distance for force. And this is dealt with by the lengths of the arms. If we've got the effort arm divided by the load arm as your mechanical advantage. So if we've got, let's say, this situation where this is, let's say, 3 meters and this is only 1 meter, the mechanical advantage of this is going to be 3, right? 3 divided by 1 gets you a mechanical advantage of 3. However, looking at this, if this is going to come down with, let's say, 10 newtons of force, and it is going down 1 meter because it's not the full length of the arm, this is going to come up with 30 newtons of force. So we're gaining force. However, because this arm is 1/3 the size, you're only going to get 1/3 of a meter in terms of the actual height lifted. And so the amount of work done, force times distance, this would be 10 joules of work. 30 times 1/3 is also 10 joules of work. We got the same amount. We have traded distance, right? We put in a full meter of distance, gained only 1/3. We've traded distance for force because we've only used 10 newtons of force, but we've gained 30. These next questions I would like you to try. This deals with, again, what's happening with mechanical advantage based on effort and load. But what we notice here is that the change of the force at the load is always a multiplication of the mechanical advantage. However, the change in speed is always the inverse of the mechanical advantage. So mechanical advantage of 2 means you're gaining twice the amount of force. However, you are losing half or divided by 2 of the speed. So give this a try. Pause the video, give this a try, and we'll be back in a moment. Okay, so here we go with the answers. Check to make sure that you've got these right. If you just didn't get them right, you gotta ask some questions. Please ask questions. So if we take a look at the two questions below here, well, what happens if we've got 200 Newton force applied at the 12 centimeter effort arm at a rate of 3 meters per second? What is the force and speed of the 6 centimeter load arm? Well, first thing we're going to do is we're going to figure out what that mechanical advantage is. And that's just the length of the effort arm divided by the load arm length. And so we've been told that's 12 divided by 6, so this has a mechanical advantage of 2. Right, which means the change in the force is going to be twice the amount. But the speed is going to be half. So if we had applied 200 newtons of force, we actually wind up with 400 newtons of force at the load. However, the 3 meters per second divided by 2, it's only going to be moving at a rate of 1.5 meters per second, right? So we have gained force, but we have lost distance. What happens if it's the other way around? Well, in this case, the mechanical advantage, again, is 6 over 12, which generates a mechanical advantage of 0.5, or 1/2, because what we've done is we flipped this around. So this, what's happening with the force is we're taking the 700 newtons that we're applying, and we're multiplying it by 0.5, which 700 multiplied by 0.5 is 350 newtons. The speed, however, is going to be divided by 0.5. which we're going to take for 5 meters per second, divided by 0.5. That generates 10 meters per second. Now, this really is using the same class 1 lever, both sides. We've got a lever here with the fulcrum, where this side is 6 centimeters. And this side is 12. Okay, if we had, with the first scenario, what we've done is we've applied the force on this side. So we gain a mechanical advantage. We're gaining force on this side. However, it's moving in a smaller speed, because here what we're seeing is the shorter length. In the second one, what we've got here is we're actually applying the force on this side, gaining the force on this side. Now, we lose half the force, but it's happening twice as fast, and that's the scenario in the second one. So, class 1 levers always are going to increase force. Class 2 levers are always used to increase the load force. You're always going to see a mechanical advantage greater than 1, because the load arm is always less distance than the effort arm. Where in that class 3 lever, you're always going to get a load that is smaller than the effort force, because in that case, the effort arm is always shorter than the load arm. So the advantage of having a class 3 lever is that you've got a greater distance, a greater speed, even though you have less force acting on the object, right? And so it's a speedy lever. Class 3s are always speedy.